This was not the last question where it's asking for you to leave questions. This was one of the questions that I had here. It said, explain in your own words why we cannot use the original ice chart from Part A and Part B. And just to refresh your memory, Part A gave you like to write the expression. Part B was where, okay, now we have this weak base, and I think it's aniline, yeah. And so we have our conjugate of our weak base, which acts like an acid, and the other product, which for some reason I didn't show water. That's bad. Water. Okay, dash, dash, dash. All right, so water should be in that, especially if we're making hydroxide. So when we look at this, we cannot use this same ice chart when we add HCl, because here's one of the explanations. We may not use the original ice chart because the original had hydroxide in the product side, or on the product side, which would be ideal if there were a base that was used for this titration, or maybe we were titrating it with a strong base. However, in this case, there is a strong acid, which dissociates into hydrogen ion, so we need the hydrogen ion in our product side and not the OH. And I love that answer. So the reason why is because we're adding a strong acid, which is our hydrogen, and so we have to have our ice chart different. So what that means is these guys flip sides, and we put hydrogen on this side. Okay. Another one was we cannot, because the molarity of the aniline at equilibrium has changed due to the inclusion of 5 milliliters of hydrochloric. So I'm not real excited about that, but I am excited about that. Okay, so as long as there was something mentioned about the hydrochloric acid, that's great. This is true. Once that liquid was added, the molarity of everything in the solution or in the beaker will change. And that's one big difference between titrations and buffers, is that when we add a solid, we say that the volume isn't going to change because it's going to dissociate pretty well. But when you add a liquid to a liquid, it's hard to ignore that fact that the volumes are going to change. Another one, because the original ice chart deals with the hydroxide and not hydrogen, and we are adding a strong acid. Awesome. Okay, so those were great explanations. I gave you credit if you mentioned something about hydrogen being added and instead of having a hydroxide. All right, here was one of the questions. Why was the solution not considered a buffer? Pretty good question. And when we look back at the ice chart, actually that's not the right ice chart. Maybe, here we go. Let's look at this guy. So here's our problem that we worked out, and I actually have it online. So we set up, we had the weak base, and then we found out what the pH was, and then we added our strong acid, so we added hydrogen. Let me ask you a question. Looking at the initial concentrations of these three things, would that make a good buffer? And why? Yeah, if I look at these concentrations, mainly I'm looking at these two concentrations, but if I'm looking at those two concentrations, would this solution initially be a good buffer? No? Why? What makes up a good buffer? We want big numbers here, right? I mean, that's not a real big number, but it's definitely bigger than that number. And if we had, say, at least maybe a 0.08 there, if we had that, would that be a good buffer for this solution? Yeah. But what we don't have is we don't have any initial amount of the conjugate of our aniline or our weak base. So when we look at buffer solutions, again, keep in mind that, true, we are focusing on the hydrogen or the hydroxide, but more importantly, we're looking at these guys. We want to make sure that those concentrations for our weak acid and its conjugate, or the weak base and its conjugate, has stuff in there. We want to make sure that we have enough to whether it reacts with hydrogen or hydroxide. A good buffer can handle either of those, hydrogen or hydroxide, if we add that. Okay. And I like that question. That was a good one, because I guarantee you that person that asked it wasn't the only one. So why was that not a good buffer? Because we didn't have large concentrations of our weak and its conjugate. And that's a good way to put it. The weak and its conjugate. Okay. What's that?
Oh. What's the girl that says her name, Kelsey?
Yeah.
The last question sounds like one she would say.
This one or this one? This one?
Yes, yeah.
Oh, okay.
Yes, that.
All right, so everybody good with the buffer. I'm glad that you're reading ahead. Thanks, Sam, for paying attention. That's great. And that's on tape now, or on the video now.
What? Oh.
Yeah, I'm doing it for Kelsey, Jordan, and I thought there was somebody else going too. Who else is missing?
Kelsey, was that your question?
No, it's not. This one, is that the one you're referring to?
Yeah.
Yeah, he's here today.
I'll take it. My second guess.
All right, when do we use a new ice chart? That's a good question. Okay, when do we use a new ice chart? Well, we use a new ice chart typically when you start off this way, and you're like, okay, well, I've got a weak base and hydroxide's produced, but then I go and add a strong acid, or yeah, if I start off with hydroxide, I add a strong acid, then I have to have a new ice chart. If I start off with this and add a strong base, do I need a new ice chart? No, because I have hydroxide. Okay, so it's when you have a different thing here. Now these will always be the same, regardless of whether we add a strong acid or a strong base. Okay, now I'm talking about these, not the numbers. So when you need a new ice chart is when you start off with a base and you add a strong acid. And notice how these flipped, okay? Because we want to keep it respective of where it's going, where the hydrogen's going, or where the hydrogen's going, okay? All right. Now my mind is officially blown, Mr. Craig, officially blown. What are the differences between all the types of problems in this chapter? I cannot seem to differentiate between them. Good question. The first part of this chapter, we started looking at just weak acids and weak bases, and that was it. And then we started to add something to those weak acids and those weak bases, which were what? Salts. But at that time, when I was adding those salts to the weak acid and the weak base, I didn't call it a buffer. But really what you were doing is you were building a buffer, or making a buffer. We didn't know if it was good or if it was bad, but we were making a buffer. With titrations, you can build a buffer system and then titrate it, but let me ask you this. Looking at this example problem that I gave last night, is this a buffer solution? So let's start off with what we've got here. So we've got our weak base, okay? Is that a buffer?
No.
No, okay. Then I titrate it with a strong acid. Is that a buffer?
No.
No. And then I want to find out, okay, at the equivalence point, is that a buffer?
No.
No. And the way that you'll know that you're creating a buffer is because you're going to add a salt. Okay? So if you have, and just adding a strong acid or a strong base doesn't make it a buffer. But in this case, this system is handling it because this is a base, this is a base and this is handling the hydrogen. So with titrations, we don't really care if we have a buffer solution. Now the lab that we're going to do will be a buffer solution. That'd be pretty cool. You'll like that one. Okay. So that's a good question. Sam, you really didn't want to take credit for that?
That wasn't my question.
No. Yeah, Ishmael.
Are salts always
Wait, who was it?
bases?
No, salts are always 100% going to dissociate.
Squishy?
Okay. And then we have to look at what's on the front end. So if this is a conjugate of a strong base, then it's a base. If you have your salt and there's a conjugate of a strong acid, then we've got that salt's going to behave as an acid. Yeah, Rishi.
So titration is just when you're wanting the moles to be equal
Yes.
of any. It can go either way, right? Like the base equal to the acid, or the acid equal to the base.
Correct. And what we'll do in the lab is we will get it to its equivalence point, and then we'll exceed it. And you'll see how that titration curve looks like. Did I talk about titration curves yet?
You had the equivalence.
It was in the video.
That's what I was referring to. I couldn't remember if it was this video or that video.
Yeah, you had it.
Okay. I thought I talked about it, but I didn't remember if it was the first one or the second one. Okay. And we'll definitely talk about titration curves. If not today, definitely the next time, Monday. Okay. I like this question. actually not a question, but a statement. I would just like lots and lots of practice with this. Your wish is my command. Okay? Don't worry, I'll get you a lot. I don't understand why we can put together the amounts at the beginning of Part D to find the total volume that we need. I understand why we can put together the amounts. Let me look. Part D. Why we can't. Okay, Part D, it's asking for the equivalence. Oh, okay, let me clarify the difference between Part C and Part D. Part C, like what you're going to do on the lab on Wednesday, is, well, you won't add 5 mils. You'll actually go as the pre-lab suggests. But what's happening is we're going to assume Part C and Part D, you're starting over. Not really, but we're actually adding a certain amount of the strong acid or strong base. So the Part C, typically on the AP exam, they ask this question hoping that you recognize that we're not at the equivalence point, but it doesn't ask that question here. You know that it's the equivalence point when the moles of the acid are equal to the moles of the base. Now, that's why Part D looks so innocent. It's just that little statement, at the equivalence point, determine the pH. But when we look at these things, yeah, true, we put 5 mils in and then we add more, but we really want to focus on the total volume because we're adding a liquid to a liquid, which changes the molarity. Yeah, Timmy?
Why don't we have like OH in there?
Why do we have OH in there? Don't, okay. Well, again, it's really small here, actually really, really small, times 10 to the -6. And as soon as we add any hydrogen, well, in this case, we're adding a strong acid, so it's trumped right off the bat.
Could I rephrase it, please?
Sure.
Why don't we use the same ice chart as we did for Part D?
Somebody else answer that for me. Why would we not use the ice chart we did in A as we did in B?
Reproduce the one in
Yeah, so we have this one, whoops, that one.
A. Because that has OH on the product side, but you're adding acid, and an acid disassociates into an H plus ion, and you need an H plus in the product side if you want to solve the problem.
Let me ask you this, Timmy. Is this thing acting as acting as an acid or a base?
That is acting like a base.
Okay. How do you know?
That's conjugated to Ka and
It's got a Kb. So we know that that's going to behave like a base. So that's why we have the hydroxide. And the initial part of this question was asking, okay, well, what is, it gave you the pH, which is on the basic side, which means that this is really low. And we can't use the same ice chart because, just like Rushi said, we're adding a strong acid with a much, much higher concentration than the hydroxide at -6, where this is like -2. So this is a much higher value. And we're adding something that's strong. So anytime you're adding a strong acid or a strong base, make sure that that strong acid or the strong base is on the product side, which means flip those guys. Okay. Did I answer the one question that was asked? Understand why we can put together. Oh, I don't know if I did that or not. Did I answer that?
No.
Okay. So you can put them together. This is, I believe, the first part where we're not at the equivalence point. So we have to find out what the total volume is to find out what the molarities are. So we want to do this calculation here, find out how many moles to see if we're at the equivalence point. That's really when you can tell that you're at the equivalence point, when the moles are equal, not when the molarities are the same. So the reason why we have to do the second volume, well, we don't need the second volume initially, but we need to find out what the molarity is after we have those same number of moles. So we're going to add a certain amount of the titrant, in this case it's the strong acid, to that beaker that has the weak base in it. So, and I don't know if you had a chance to look at the write-up yet, but here's what we're doing. We're going to be adding some titrant. In this case it's a strong base, and we've got our strong acid that's in here. And as soon as I open up that valve, then some of the base is going to go in here and cause the level of that liquid that's a PDF file. So it's going to cause that level to increase a little bit. So when you add a liquid to a liquid, we have to be aware of the volumes. But when we add a solid to the liquid, we just say it's negligible. We don't worry about it. So so we have to be really aware of what our volume is, because that does change the molarity significantly. Okay. And at the equivalence point, once you have the same number of moles, shouldn't the molarities be the same? Yeah, I mean, you've got the same number of moles, you've got the same volume, so it is the same in this case. Okay. All right. How do you know if it's a titration, or wait a minute, how do you know if a titration isn't a buffer solution? Is a buffer solution the addition of a solid and a titration the addition of a liquid? That's huge. Okay. Generally speaking, when you add a salt, it is a solid. When you're doing a titration, you're adding a liquid. Okay. So when we look at whether we're investigating something, and I think most of the time the question might say something along the lines, in this titration, or something about titration. So sometimes when we do a titration, we might add a salt and then do the titration, like our lab is going to be. Or in some cases, we just go straight to this part right here. Okay. You will never add a solid in a titration. Okay. In other words, once we have our weak acid or weak base in that beaker, we're never going to do titration with a solid. It'll always be with some strong liquid, whether it's a strong acid or strong base. All right, one of your last statements was about how, before this lesson, we added solids to the solution, so were you referring to buffers? Yeah, I like that. Okay. And your phones are getting close up. All right, why change to milliliters? And again, since this is a titration, we want to make sure that we're keeping track of our volume here. And again, this is pretty much what I just showed you a second ago. So we have to make sure that we're aware of the volumes, because we want to find out what the molarity is. And then D, confused on how you got hydrogen to start as 2.5 times 10 to the negative 3. I think that was the number of moles. So again, we had our volume, we had our molarity. If you know the volume and you know the molarity, always start with the volume and then multiply it times the volume, the molarity, to get the total number of moles. And we're going to do some more with this today. Okay. Were there any other questions? I know that some of you were a little late getting your answers in. I was actually putting this together at lunch. Ishmael, did you have anything to... Okay.
No questions.
No questions. You good? Okay. All right. So let's take a look at day 93, the homework here. Sam, did you have questions? Or are you just dreaming about titrations?
I put concern. When you said, do you have any questions or concerns? I said concern.
Concern?
And I said, I don't even know what I did these last 41 minutes.
Oh, I do remember. Was that you that was distracted? Somebody said that they got distracted.
I wasn't distracted.
Oh, Matt, okay.
I was too late. I was like, I watched the whole thing. I just did, and I was just like, write it down. I just didn't know what I was doing.
All right. Well, that's what we're doing today. All right. So looking at day 93, part F, the homework. So it's not an example. Yeah, go ahead. Hang on.
And the first page just said there were some questions about the lab procedures. What kind of AP questions?
What was this? Oh, okay. Let me pull that up. That's a good question. All right. That was examples part 1, right, Taylor?
Yes.
All right, let me talk about this real quick. And it's good that we're doing it now, and not after the lab, so you can actually kind of pay attention while you're doing the lab. All right, so at the bottom of the first page it says, frequently questions appear on the AP exam that deal with the procedures of the titration or 4 titrations. One procedural question has appeared more than once that involves the cleaning of the burette prior to the titration. So what that means is the burette is actually, hang on, I'll grab one. Here's the burette. And it's an interesting looking piece of glassware, and this is probably one of the more expensive pieces of glassware that we'll be working with, and they break really easily, so be careful with that. But the burette actually has the markings in reverse, so 50 is down here, 0 is on the top, and this is in milliliters. And also it's very, very precise, let's use that word, in that it marks off tenths of a milliliter. Okay, so it marks off tenths of a milliliter. So we'll fill up our burette with our, in this case, we'll be adding a strong base. And one of the things you don't want to do is you just don't grab the burette and go, okay, let's fill it up and let's go. Because you don't, number one, you don't know what was in this beforehand. We could have had a strong acid, or we could have had a different type of base with a different concentration, and there's residue left over. So the first thing we always do is we run distilled water through it. And sometimes the valve gets a little gunked up and we need to take it apart, and hopefully that'll be ready to go for you guys on Wednesday. But then you put in the base, the actual base, and run all of that out. So we'll put in probably, I think it's between 20 and 30, I can't remember, it's on the instructions. And then we set up our burette for the titration by adding the base that we need. Because again, if you're not sure what that burette was used for earlier, then it could have other residue in there that could affect your lab results, and especially with the things that we're going to be doing where the amount drop-wise, and who remembers how many drops make up a milliliter? Nobody's done pre-lab yet. There's 20. Okay, there's 20 drops make up a milliliter. So in some cases, it might be down to 2 or 3 drops, and you'll trust me, when you see it, you'll know it. You'll go, oh my goodness, that was pretty close. So one of the things that is often asked on the AP exam is, how do you clean your burette? How do you get the titration ready? Do you just grab it, go, fill, and bam? No, take care of it. So we run the distilled water, should be rinsed with the solution that's going into it, run it out, and then fill it up. Okay. Good question, Taylor. All right, so getting back to this, benzoic acid, and there's the formula for it, is a weak acid, reacts with water according to the reaction represented above. Write the equilibrium expression. Do it. Speed things along here. All right, let me ask you a question. See what I did? Is that okay?
Yes.
And that is okay. Okay? Keep in mind that these two things represent the same thing. Okay? Those are the same exact thing. Yeah, Rishi?
Is there a final multiple choice?
It's all multiple choice. Yeah. And I'll give you the review packet. I actually have it over here, but I don't want to stress you out just yet.
All right.
Timmy, what's wrong with things?
Those is gum.
Timmy, what'd you have for lunch? Why do you need gum so bad? You have garlic? You gonna kiss someone after this class, or? All right. So everybody's good there? Good. B. A sample benzoic acid is dissolved in water to produce 55 milliliters of a 0.25 molar solution. Okay. Now, here's what I don't want you to do. I don't want you to look at this and go, oh, since that was dissolved, that's a buffer. No, this is still our benzoic acid. So it's just telling you how they made it. What's more important is I even gave you, or the question gave you the amount volume-wise and the molarity. Okay, so don't read into this question by saying, since it was dissolved. What I'm talking about is we have our solution is already made, and then we decide to drop some solid in there. Okay, that's not what's happening here. Okay, we don't have our benzoic acid in here and then we're adding something. This is just the procedure of how that was created. Okay. All right, so the pH of the solution is 2.4. Calculate the equilibrium constant. Again, that should not be difficult. And you might, and was it Rushi, was it you that had your mind blown? Notice how these things are the same thing. Was it you? The mind blown? Good. So, again, let me ask you this thing. Do we care about the volume in Part B?
In Part B, no.
Why? Because Timmy said no? Why? Why do we not care?
Because we already have the concentration.
Very good.
But we'll need to know it later.
Yeah, isn't that dirty? How these questions are set up that you don't use the volume here, but you have to know it in C or D? Yeah. So that's mean. Do we know X?
Yes.
Yes, because we know the pH. Okay. So we know what X is. You can do an ice chart, yeah. I'm not going to, but you can. All right, well, shouldn't have done that. Can we use 5% for this? Don't even think about it. So anybody get like 6.44
times 10 to negative 5.
-5? Timmy's on his A game. Okay. Nothing new, nothing difficult there. Okay. Part C.
What was the answer?
I don't know, Sam. What'd you get?
6.44 times 10 to the negative fifth.
-5. I like that. Good.
You could have just screwed up.
I was checking to see if you're doing your work. Keep you honest. All right, Part C. The solution prepared in Part B is titrated with 0.1 molar sodium hydroxide. Let's stop right there.
You can't use the same ice chart, I mean the same, is that what you're gonna ask?
I like what you said, but I was going to ask, is this a buffer or a titration?
Titration.
Is this a titration to a buffer?
Yes.
No.
It's a buffer to a titration.
How about a titration to a buffer?
No.
Are we titrating to a buffer?
What? No, it's titrated with a buffer.
So there's a buffer in this?
Yes.
Where? Let's go back up. Okay. So what is Part B dealing with?
Liquid?
Isn't it just titration without a buffer?
Correct. In other words, here you've got your benzoic acid. It shows how it dissociates. It says it has a certain pH. No salt or solid has been added to this. Okay. So this is just a titration. No buffer.
What about a strong base?
This is a strong base. I like that. Hey, Ishmael.
Wait, can the salt be a liquid?
It can, but it won't.
Oh.
Yeah, we won't do that, and I've never seen that on the AP
Would
exam.
there be a buffer during titration?
I guess my main question is, do we have a buffer here?
Yes.
No.
Why?
Rushi.
Okay, so, separate question going on Ishmael. So if there was a liquid salt that was
Mhm.
added, would we have to take the volume into consideration?
Yes, but that's never going to happen in here. And the only time that that salt would be a liquid that we would care about is if it were molten, and those are really high temperatures, and if you put high temperatures in a solution like this, it's going to vaporize the water and the acid or the base. I mean, if you think of sodium chloride, don't think of it as aqueous sodium chloride, think of it as a liquid, pure sodium chloride liquid, which is kind of nasty. But we'll always be working with salts, and most ionic salts are solids at room temperature, or even at the boiling point for water. Yeah, even at 100 degrees, most of them are still solids. So, good question, but no
Why
liquids.
does this have a buffer?
Well, let's look at the consideration for, and I didn't draw an ice chart, and I probably should have, but let me do a generic ice chart here. So we have our HA and our anion. Okay. So initially, how much of this do we have?
0.250.
How much of this?
0.
This?
0.
That right there should tell you. It's
What?
not a buffer. That right there should tell you.
Oh, okay.
And then, so we don't even have any of that information. So right there, that tells us we don't have a buffer. And going from B to C, we're just titrating it. Okay. So let's see here. So the solution prepared in part B is titrated with 1 molar or 0.1 molar of NaOH. Calculate the pH of the solution when 5 milliliters of the base is added. So what do we do now? This is, part C is the new stuff.
Don't we show
Wait, I think I know.
Do we show this?
Really?
Yeah.
Can I go there? Am I going to be on video? Okay, so we had to make a new equation, right?
Yeah.
So it'd be Am I doing this right, class?
Now,
Boy, oh, dang it.
now,
What?
don't we show the dissociation between the strong base?
Oh, do I have to write that first?
You can write it above, it's fine.
Oh.
I will tell you, Timmy, you don't have to. I'm going to assume by this point you know what the strong bases are. If it's a salt, I would like to see that dissociation.
Isn't that salt?
Sodium hydroxide technically is, but in this case we're treating it more as a strong base. So if you're looking at precedence between a salt and a strong base or a strong acid, I want you to go with the strong.
And then we will make an ice chart. And I haven't gotten too far, but we already know the concentration of this, which is 0.250 m. And then we can't find this. And then this is approximately 0.
Yeah.
So, and then we can find the OH by taking this,
I hope you guys are using a pencil.
and wait, am I doing this right?
Not yet.
Not yet. Why didn't you stop me?
You sounded so confident. And everybody, and I'm looking at everybody, and they're all writing things down.
Oh my God.
I don't want to stymie your enthusiasm.
My bubble has been bursted so badly.
I'm going to keep your ice chart.
Wait, is this on video?
Oh God, yes, it's on the video. Yeah.
It's C7H5O2.
Wait, did I do that right?
Oh yeah, you did this right.
Oh, that's good. I got something right.
Go ahead, Timmy. What?
Is it not approximately 0? The C7H5O2.
This
What
one?
did I do
Yeah.
wrong?
Yeah, it's approximately 0. But
How do we know?
what do we do differently with titrations?
Don't
Moles.
you do that milliliter?
Find out how many moles we have. Okay, that's the first thing. And your heads up on that is that we've got a volume and we've got a molarity. Okay? We have a volume and a molarity for the strong base, and we have a volume and a molarity for our acid. So we have to find out how many moles we have, because again, we're adding a liquid to a liquid. Okay,
Wait,
so,
that's what I was gonna do next,
but
to find the concentration.
let me ask you this.
JK, no, I wasn't gonna do that.
So if you had 0.25 molar and I add some strong base liquid-wise, is that molarity going to stay the same? Let's assume that the hydroxide doesn't even react with it. Would the molarity stay the same?
No,
Why?
because there's a different concentration, or there's more liters.
Yes, volume. Good. Good. So there's a different volume. So we want to find out how many moles of each we have. So we can start off, and it doesn't matter if you start off with sodium hydroxide or if you do the other one. Sorry, Timmy, let me do this for you. Hydroxide. So we have 5 milliliters and 1 liter, and the molarity was 0.1, and that'll give us some value. And then with the acid, we have 55 milliliters. So I'm just going to go HA. So we have 55 milliliters.
Do we have to show that chart?
Yes, I want to see this. And the graders want to see it as well. They don't want just magic numbers to show up from out of nowhere. Okay, so let's get our moles here, and then I'll ask another question. So that's what, 3 zeros? And this will be with, whoop.
I hate titration.
No, you don't.
It's like,
No, I'm pretty sure I do.
Is it 013? Yeah. Okay. So we have our mole amounts. Are we at the equivalence point?
no,
Why, Sam?
because the moles aren't equal.
The moles are not the same.
I was confused in the video how you got the moles to be equal.
We'll get there in a second.
Mr. Craig,
Yeah.
so what has to be equal? The OH concentration?
The moles of your weak and with the moles of your strong.
Gotcha.
So your acid and base need to have the same number of moles.
Okay.
Yeah. And what I'm saying there is, it's kind of making it, because sometimes we'll have a weak base and a strong acid. So that's why I'm saying the moles of the acid have to equal the moles of the base.
Okay.
Because if I have enough of this hydroxide, then that hydrogen is going to jump on there and make water. And that's one reason why I want to use the conductivity probes, because how good is pure water at conducting electricity? If I had a bathtub and I filled it up with pure water and I put you in it, okay, and I take a toaster and plug it in,
We would die.
and I said, "Here, Sam, catch,"
I would die.
you wouldn't.
Well,
Pure water does not conduct electricity. Tap water does, because it has chlorine, fluorine, fecal matter, all those things that love to carry electrical charge. We should.
I'll give
We should
you
put
pure
sand.
water.
But the good news is you're going to see it during the titration. Does not conduct any electricity. Okay? Do hydrogen ions conduct electricity? Do hydrogen ions conduct electricity? Oh yeah. Do hydroxide ions conduct electricity? Oh yeah. Put them together. If that's the only thing in the solution, nothing. Okay? And we'll see that. And what's going to be really cool is when we get to our equivalence point, the conductivity is going to be 0. Or very, very close, depending on how good you are. Yeah, Timmy.
Why don't we use the same ice chart as we did for?
Wait,
Are you still talking about this ice chart and that ice chart?
who's like,
Sam's ice chart?
Yes.
Ooh. We have hydroxide.
you still die.
We have hydrogen. So we're starting off with a weak acid, and that's all we had.
Well, I was looking for pH though.
Yeah, we did that already. This is asking for pH?
No.
Oh, yeah, we never found a pH for that. So take the negative log of this. Sorry. So what'd you get for the pH? Yeah.
We're given the pH.
We were given the pH?
Yeah, you eat.
Oh, Timmy.
No, it said calculate. No, part C.
Get just
It said
go away.
Calculate the pH.
Bubby, we're just getting started.
Yeah, but
We're not even there yet.
why don't we have
I'm still trying to get to Sam's part. Let me get there.
But why don't we have hydrogen on the product side of C?
Why do we have what?
Why don't we have hydrogen on that?
This is we're adding strong base, sodium hydroxide.
That was the question on the video, like.
That was the same question Timmy asked like
Yeah, it's the
10 minutes ago.
Yeah.
When you caught that piece of gum, did it hit you in the head? Concuss you? Oh my God. All right, so we need to find the concentrations of these things. So what is our volume?
Our volume is 60 milliliters
60 milliliters. How'd you get that?
because I added up 5 and 55, which is equal to
This guy, I'm watching this guy. So, and I'm going to speed it up a little bit. Is that equal to 60 milliliters? 0.0. Okay, so we'll get a value there. And Sam, I'm going to move your ice chart down a little bit further. But don't worry, you're coming back up. You're going to get redeemed here. Oh, 0. All right, somebody give me some numbers for these.
For the 0.00055 by 0.06, it's equal to 0.008333.
Is there 1 0 or 2?
2 zeros,
Okay. And then the other one?
almost there. It's 0.216666.
Point. Say that again. 2. 0.2.
6.
6 repeating.
Yeah.
Okay. All right. So now we have our molarities. Sam, come on back.
Stop me from making food. Wait, I don't even. I raised my.
Oh.
Wait, no. I
Okay, I have a question.
just like being up here.
How is C7 like K502, what's it called? How would that be approximately 0?
How's that approximately 0? Hang on, Sam. Because back here, looking over there, our anion, just the A minus,
Yes.
that's 0. When it establishes equilibrium, then it became to this concentration here. So since we get to use 5% rule, then we'll do that.
Wait, can you state that?
Okay. Our anion, the C7,
Yeah.
all that jazz, is here. We don't have any amount.
Yes.
So at equilibrium, it's this amount here.
Yes.
So we can ignore that because we're going to use 5% rule.
Okay. But could we put the 3 point?
I wouldn't unless you want to use the quadratic
Oh,
equation.
wait. I just realized something. So
Yeah.
the two concentrations that we just figured out, would that go right here and here? So this.
Got it.
So this would be 0.00833. Oh, that's really bad handwriting. Okay, 0.0. And then this would be 0.216. And then this is
Good.
a
Yeah, we'll say it's approximately 0. Even if you put a 0 there, it doesn't change anything because it's still 5% rule. But it's good to have a approximate.
And then we'd subtract this
Why?
because this is smaller.
We subtract the smaller of the two. So, yeah, we'll leave it at that. Somebody give her some numbers here,
Yeah,
please.
numbers.
Here, you can do the hydroxide while you wait.
I got you. 0.0.
Oh, better hurry, girl.
Wait, what? What? Which one? This one?
That's 0.
No.
Oh, yeah.
Wait, isn't that approximately 0? Okay, and then 0.2083.
Stop. We're good.
So then this one is, oh wait, negative point.
Oh, wait.
Positive.
Okay.
0.00833. So now,
Can we use Henderson Hasselbalch for this?
Yeah,
I have a question. Wouldn't hydroxide be approximately 0?
We're gonna solve for it, yeah.
Wait, is the Henderson-Hassel block for buffers?
Could be, but it also could be used in this situation.
Why? Because
Good
we have
question.
a H,
No, we
or
don't have an
A,
H.
an A minus and a HA
Yep,
and a P. Oh.
and we're looking for pH.
Oh, so can I do this too, class? Can I do this?
No.
Because I'm.
Go, Sam, do
Okay.
it. Change the color though.
Okay. Oh, I hope everyone had what was up there already.
Here, I'll give you the equation. pH equals.
No, I already know it.
Oh!
Isn't it A over
Very good.
HA?
Yep.
So the pKa
We found it earlier, which was.
is the negative log of 6.44 times 10 to the negative fifth plus the log of. So A is this one? Oh wait, no. Wait. A.
Take a look at your ice chart.
So A is the negative one. So A would be this one.
Yep.
So 0.00833 over, and then 0.2083. Roshi, you want to do this? You're my calculator boy.
Well now, so we have a title. Come on now, calculator boy.
Wait, what are we looking for?
Yeah, what are we looking for? That's
Take the
good.
negative log of this plus the log of this divided by this. Any day now, Roshi?
Alright, I got the pH to be, is that what you're looking for?
Yep.
pH, 2.79.
pH equals 3.72.
Two. Dose.
Dose. C.
2.79. So, this is. Okay.
Yeah.
So that.
Why would you use 0.2083?
What is that?
Why would you use the 0.2083?
Because that is our benzoic acid, if that was
I thought you were
subtracted.
supposed to use initially.
No. In this case, we're looking at the equilibrium. When you're doing a salt, yes. So in this case, if you add a strong, and that's a good point, whenever you add a strong acid or strong base, we will have different concentrations here. Jordan's blowing my phone up.
So, that's the answer. Part C. Oh, dang it, now I have to write all this down.
So 2.79? Yeah, I like that. Okay.
Well, until it gets.
Now I'll leave that up there, and actually, how are we going to know? Here, let's see here. So do we care about the number of moles for our sodium hydroxide if we were trying to answer part D? Or I'm sorry, let me rephrase that. When we look at the question, do we care about the number of moles of the sodium hydroxide, or do we look at the information from the benzoic acid?
Benzoic.
Correct, because what we're always going to do is we'll have our weak whatever, and we're going to add our strong. Our strong will always be in the burette. So we want to make sure that we're adding the correct volume or the same volume that we have, same number of moles of the base or the strong acid that we are adding to our weak. Yeah, Rishi.
So we're calculating the number of, or the volume of the weak acid?
Yep.
Or weak acid
The moles of the weak acid. So
that is needed?
do we already know that value?
Yeah.
Where is it?
Point 0.01. Why?
It's right here, right?
Right.
So this is our, in other words, when we look at it, we're trying to ask ourselves, okay, when we prepared our acid initially,
Right.
how many moles did we have in there?
0.01375.
There you go. So at the equivalence point, so if we know that our HA is equal to 137, is it 0?
Yeah.
All right. Then our our sodium hydroxide, or our OH, needs to be
0.01.
the same thing. Now, this is a little different because, true, we know how many moles we have of each, but we need to figure out how much of this is 0.01375. So we got to find out the volume that we need to add to get to that. So there's a couple things that's kind of neat about this. We know what that's important here. Let me scoot this guy down.
Wait, hold up.
Okay, go ahead. Are you still holding up on that, or?
No, how'd you get 0.01375?
Okay, let somebody else answer that.
Okay, so initially when you have in the beaker, you put, so start from the beginning, you had the strong acid and you pour water in it to form a solution. Now that the moles, that remains constant, but you're trying to find the amount of moles needed of OH to counteract the base.
So how'd you calculate that?
I found this from way back in part B. Again, that's what I'm saying about these questions. They're dirty because they hide the information up above. So we aren't using the volume for this until we start the titration process. But we need to know how many moles this actually is. So whenever you see a titration type problem and you see this some weak whatever, I would immediately find out how many moles that is, find out, okay, I've got a certain number of moles, and just like highlight the crap out of that. Okay, so that draws your attention in all steps.
Wait, so then why is that for both AJ and
Yeah.
OH negative?
This is, oh, okay, so at the equivalence point, good question. So we know that this is how much we have. At the equivalence point, how much base do we need to have to get to the equivalence point?
But why is hydroxide the same?
Yes.
Okay, what is the definition of the equivalence point? Look in your notes real quick.
I know, like the acid and base are equal to each other.
Moles of acid.
So there's more moles of HA than what's right there, but we just are saying how much of that we need, so that's the same as OH?
Yeah.
Because there's less OH
But,
than
like,
HA.
In part C, there was less because we only added 5 milliliters. So we were starting the titration and we're like, okay, are we to the equivalence point yet? Well, based on our number of moles, no, we're not close yet. So we got to keep adding more of the base in this case. But if you wanted to start right off the bat and say, okay, I know I have this many moles of my weak acid, and I know I need X number of milliliters of my strong base, I can just turn that thing on and let it go, and then stop it right about a milliliter or two before you get to the equivalence
Why
point.
do we use 0.01375?
Because this is our moles of the weak. That's our guiding light for titrations. Whatever your number of moles is for your weak, that's how many moles of the strong you must have to reach the equivalence point.
Okay, agreed.
Yeah, whatever the moles of the weak are, that's how many moles of the base we need to get to the equivalence point.
Base, use the moles of the weak base. For
Then you look for you're going to need that many moles of the strong acid. But more importantly, we know that this volume is 55 milliliters, right?
Yes.
How do we find the volume of the hydroxide?
Isn't it?
What do we know about the hydroxide that's important?
5 milliliters.
No, we don't care about the 5 milliliters because we're trying to find volume. But we know the molarity. And the units for molarity are what? Moles over liters. Okay? So if I know my moles that I'm trying to get rid of it, I'm going to move moles down here, liters go on top. Whenever you look at molarity, the number that you have for molarity always goes with the unit moles. So in this case, what is our molarity? 0.1?
Yeah.
Okay. And then if I want to find out how many milliliters that is, just for kicks and giggles, I guess, then we can put our milliliters there and then solve. Okay. And we actually do need the number of milliliters because we're going to add the volumes together. And then whatever that equals. 1,000?
Or wait, 100.
130 or 137 and a half?
Yeah.
Okay, I like that. Okay. So there's how much. So this is a 50 milliliter burette. So we get to fill this up twice and then almost empty it a second time, which isn't going to happen on Monday or Wednesday for you guys. So once we have our volumes, add them up. So add those together. 55 plus 137.5, and that equals what? 180, 192? Is that 0.5? Yeah. Which is equal to 0.1925 liters, if I did my math right. From there, okay, we have our moles. So we have and what does that equal? You guys are leaving me out to dry.
0.0714.
Okay.
15.
0.075.
7.5.
Okay.
15.
Oh, and now we have to do that 14 minus the negative.
No, not yet. Not yet. No, 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 no. Is that the correct molarity? Let's start off with that.
Yeah.
Okay. Now, I personally always make another ice chart just so I don't do something dumb. So I'm going to use Sam's ice chart.
Oh,
Okay. Oop. Come on. Come on down here. All right. Okay. So let me ask you this. If I have, let's go with a different color, 0.715, 0.715 dash approximately 0. What are we going to do? We have our weak and our strong
Subtract 0.4715.
because that's the smaller amount. In other words, all of these, since they're at the equivalence point, we have the same number of moles, the same molarity, they're going to react. These are going to go down to 0, and then what's going to happen?
OH becomes approximately 0.
And this goes to 0. Both of them go to 0, and then equilibrium's reestablished. And now what we've got is, whoops, the way we started, where we just have one thing at the beginning. Can you use Henderson-Hasselbalch here?
No.
Can we use the Ka value here?
Yes.
Yeah.
So KB.
Well, you have to do 1.00 times
Yeah.
10.
Yeah, we have to use Ka to find the Kb because we have hydroxide. Cannot use Henderson-Hasselbalch here because we do not have a concentration for our weak.
I have two questions actually. Ka or KB is false.
What's that?
KB is 1.56 times 10 to the negative.
Times 10 to the negative 10?
Yeah.
Okay. And then from here, we do our x squared and then minus that and solve for the concentration of hydroxide. Because we have, and you might notice on the notes, I use the letters Y here. Doesn't matter. I'm just using something different so you don't think, oh, X is what we did up in the beginning. So in this case, to find, we have Y squared, and it's 0.017, 15 minus X or Y, which we can drop, is equal to that 1.56. And then solve for Y. And Y will be your hydroxide concentration. I know we're running out of time. Y will be your hydroxide concentration, so take 14 minus that after you do the negative log. What'd you get?
P8.
pH is 8.52. Okay. So then the last question is, which of these indicators would be best for this titration to reach the equivalence point? Now again, this is the pH when the moles of the acid equal the moles of the base. So which of these indicators? And again, what we want to try to do is match up the pH to be equal to the pKa. So which one? The first one, second one, or third one would be the best indicator. And what does an indicator do?
Indicates where the
Where the equivalence point is. It does a good job. Okay. All right, so for Monday, watch video 94, the last video of the semester, and be working on your pre-lab, but we're going to do the lab on Wednesday.
Good job, Sam.